Problem set number 1, example 1.10, calculating heat transfer through conduction. So based on the problem, so in this problem, both heat for a phase change and transfer of heat by conductions involved. So we're going to find the amount of ice melted, and to find that, we're going to solve first for the net heat transferred. So this value can be obtained by calculating the rate of heat transfer by conduction and multiply by time. So again, based on the given problem, our given first is the thermal conductivity of the polytyrene foam. So is equals to 0.010 watt per meter times degree Celsius. So and our surface area of the ice box is equals to 0.950 meters squared, and the thickness of the surface is equals to 250 cm, or we convert it into meters and it turns to 0.0250 meter, and the temperature of the colder surface equals to 0 degree Celsius, and the temperature of the hotter surface is equals to 35 degrees Celsius, and the time is 1 day. So 1 day is equivalent to 24 hours, and 24 hours is equivalent to 86,400 seconds. So in this problem, we're going to solve for the mass of the ice, and we also need to solve for the net heat transferred to melt the ice. So the rate of the heat transfer conduction is given by the solution. P is equals to dq over dt, or the thermal conductivity multiplied by the surface area times the change of temperature, which is Th minus Tc, over the thickness of the surface. So since tanan na sila ay naman sila yung mga value, so we're going to insert the known values na lang, or substitute the value. So P is equals to 0.010 times 0.950 meters squared times 35 degrees Celsius minus 0 degrees Celsius divided by 0.0250 meters. So is equals to 0.3325 divided by 0.0250. So our power rate is equals to 13.3 watt. Now since we have the power rate, or after getting the power rate of heat transfer, we're going to multiply it by the time. So Q is equals to power rate times time. So 13.3 watt times 86,400 seconds is equals to 1.15 times 10 raised to 6 joule. And now we set this equal to the heat transferred to melt the ice. So Q is equals to mass times LF, and solve for the mass. So since Q is equals to MLF, we're going to both side by LF. So cancel LF. So now mass is equals to Q over LF. So substitute the value 1.15 times 10 raised to 6 joules divided by 334 times 10 raised to 3 joules per kilogram. Cancel joules. So the mass is equals to 3.44 kilogram. Problem set number 2, example 1.11, two conductors end to end. So in this problem, the heat that enters the steel rod from the boiling water has no place to go but through the steel rod, then through the aluminum rod to the cold water. Therefore, we can equate the rate of conduction through the steel to the rate of conduction through aluminum. So in this problem, so the given are in this problem, the length of the aluminum and the length of steel are the same. So ang sa given, ang nakabutang ang unit sa value sa mga given is centimeters, but dire ibutang na nako is naka convert na siya into meter. So again, the length of the aluminum and the length of the steel is equals to 0.25 meter, and their area is equals to 7.85 times 10 raised to negative 5 meters squared. And their thermal conductivity, since they're different materials, so magkaiba sila. So the thermal conductivity of aluminum is equals to 220 watt per meter times degree Celsius, and for steel 80 watt per meter times degree Celsius. And the temperature of hotter surface equals to 100 degrees Celsius, and the temperature of the colder surface equals to 20 degrees Celsius. So here we're going to calculate the temperature and the power rate of the heat transfer. So first, calculate heat conduction rate through its steel rod and heat conduction rate through the aluminum rods in terms of the unknown temperature at the joint. So first, we're going to calculate for the heat conduction rate of the steel and the aluminum rod. So first, let's calculate for the power rate of steel. So K steel times A steel times the change of temperature of steel over the length of steel. So naa naman sila yung mga value, so ato na lang sila i-substitute. But sa temperature is naa siya isang unknown. So 80 times 7.85 times 10 raised to negative 5 meters squared times 100 degrees Celsius minus the unknown temperature over 0.25 m. So the power rate of the steel is equals to 0.0251 times 100 degrees Celsius minus the unknown temperature. And for the power rate of the aluminum, so K aluminum times the area of aluminum times the change of temperature of aluminum over the length of aluminum. So same process. So substitute the value 220 times 7.85 times 10 raised to negative 5 meters squared times the unknown temperature minus 20 degrees Celsius over 0.25 meters. So the answer is equals to 0.0691 times the unknown temperature minus 20 degrees Celsius. Now after getting the two rates, so set the two rates equals and solve for the unknown temperature. So 0.0691 times the unknown temperature minus 20 degrees Celsius is equals to 0.02051 times 100 degrees Celsius times the unknown temperature. So the temperature is equals to 41.3 degrees Celsius. Now, since we have the value of the unknown temperature, we can calculate the rate of the steel or the aluminum. So let's solve the power rate of the steel. So since we have the value of the temperature, so 0.0251 times 100 minus the unknown value is 41.3 degrees Celsius. So the answer is 1.47 watt. Now check your answer by calculating the other rate. So we know that recall that the R is equals to L over K. R is the thermal resistance. So we know that the temperature of steel and the temperature of aluminum is equals to 100 degrees Celsius minus 20 degrees Celsius is equals to 80 degrees Celsius. So we also know that the power rate of steel is equals to the power of power rate of the aluminum, and we denote the rate of heat flow by P. So let's combine the equation. So PR steel over A plus PR aluminum over A is equals to 80 degrees Celsius. So P is equals to 80 degrees Celsius by add the R factors. So now we have the P is equals to 80 degrees Celsius over A times R steel plus R aluminum. So find R from the known quantity. So the resistance steel is equals to 3.13 times 10 raised to negative 3 meters squared times degree Celsius over watt. So for the resistance of aluminum is equals to 1.14 times 10 raised to negative 3 meters squared times the degree Celsius over watt. So now let's substitute these values into find the power is equals to 1.47 watt and determine the temperature for aluminum or steel rod and use it to find the temperature at the joint. So temperature for aluminum is equals to PR aluminum over A. So 1.47 watt times 1.14 times 10 raised to negative 3 meters squared times the degree Celsius over watt. So over the surface area, which is 7.85 times 10 raised to negative 5 meters squared. So the answer is 21.3 degrees Celsius. So therefore, the temperature 20 degrees Celsius plus 21.3 degrees Celsius is equals to 41.3 Celsius. So para siya dun sa solution number 1. Problem set number 3. Example 1.12. Calculating the flow of mass during convection. So in this problem, the energy is needed for this phase change. So Q is equals to mass times the LV. So thus energy loss per unit time is equals to Q over T. Q is equals to M or mass times LV, or Q over T is equals to M times LV over T. So is equals to 120 watts, and we all know that watts is equals to also to joule per second. So now we're going to divide both sides of the equation by LV to find the mass evaporated per unit time. So divide both sides by LV, so cancel LV. So our mass evaporated per unit time is equals to 120 joule per second over LV. So in table 1.14, LV is equals to 2430 kilojoule per kilogram, or it's equals to 2430 joule per gram. It's based on the table 1.4. The heat vaporization LV for water is 2430 kilojoule per kilogram. So substitute the value. So mass evaporated per unit time is equals to 1.20 joule per second divided by 2430 joule per gram is equals to 0.0494 gram per second. So convert second into minutes. So let's just multiply it by 60, which is 1 minute is equals to 60 seconds. So multiply it by 60, and the answer would be 2.96 gram per minute. Problem set number 4. Example 1.13. Calculating the net heat transfer of a person. So in this problem, we can solve this using the equation for the rate of the radiative heat transfer. So based on the given problem, our surface area of the surface area is equals to 1.50 meters squared, and our emissivity is equals to 0.97, and the temperature of the environment in Kelvin is equals to 295 Kelvin. So sa given ay naka degree Celsius, but we convert it into Kelvin na. So T2 is equals to 295 Kelvin, and our temperature of the object in Kelvin is equals to 306 Kelvin. So and the constant value of the Stefan Boltzmann constant is equals to 5.67 times 10 raised to negative 8 joule per second times meter squared times Kelvin raised to 4. So here we're going to find the power rate, or the Q over T. So let's solve using the equation for the rate of the radiative heat transfer. So Q over T is equals to Q over T, or the power, is equals to Stefan Boltzmann constant times emissivity times the surface area times T2, or the temperature of the environment in Kelvins raised to 4, minus temperature of the object in Kelvin raised to 4. So let's substitute the value. So 5.67 times 10 raised to negative 8 joule per second times meter squared times Kelvin raised to 4 times 0.97 times 1.50 meter squared times 295 Kelvin raised to 4 minus 306 Kelvin raised to 4 is equals to negative 98.53, or negative 99 joule per seconds. And again, joule per seconds is also equivalent to watts, so the final answer is equals to negative 99 watt.